Excellent. Okay. So, I'm here to talk about VMware's adventure in persistent memory, which we've had the privilege of being on since the end of 2011 with our best buddies, Intel and other companies. I'm going to restrict my remarks to x86 virtualization. So there are other technologies and other solutions, but I'll focus on x86. So we're going to talk a little bit about our experiences so far and the question, are we ready for persistent memory finally for customers and developers? And then we'll talk about some future expectations. This picture up here, I guess you really can't see it, but I'm a Trekkie, and so this is the original NX01 Enterprise. And the rule here is that after the first 3 tries, the first 3 seasons, they finally got it right on the 4th try, and then they got canceled. But hopefully that's not where persistent memory is going to end up. And if anyone thinks that the first 3 seasons of Enterprise were good, you need to come talk to me, because I don't agree. Okay, so this should be known to everyone here. We're talking about direct mapped, byte addressable, non-volatile memory that can be accessed with load and store instructions. That's what we're talking about. And we're talking about persistent memory that has latency and bandwidth that's close to DRAM, or depending on your technology, a little further out, but hey, it works. And various other things that software and operating systems expect in order to be able to manage it. This is nothing new. We've talked about this for many years. And down here at the bottom are the DIMM-compatible persistent memory technologies, such as NVDIMM-N, Intel Optane DC persistent memory, and in the future there could be NVDIMM-P. And we'll talk a little bit about that. So Andy has already sort of covered the various ways that you can access persistent memory in the native OS environments. So this is more just a reference for you, but the key ones that are very interesting for us at VMware is, first of all, what we call VPMEM disk, where basically in the guest, the virtual SCSI device is actually mapped without the guest knowledge to an actual persistent memory device. And that's all set up by the administrator, not by the actual VM itself. Then we have sort of, and you could consider, some people have called this storage over app direct, but this is basically where you're exposing, when you expose a virtual NVDIMM, a virtual persistent device, to an OS, the OS may be aware of it, but the application may still only need to be able to treat it as a memory mapped file, or a block device, and that's where this model comes in. But the exciting one is when you have direct access, and Andy discussed the various mechanisms in Windows and Linux for that. That's where you need new operating systems and new applications, and we finally have those, as you'll see in a moment. Okay, so we've been waiting for this for several years, and it finally happened. So I'm sure you've heard about Intel Optane DC persistent memory. It has fantastic capacity. Probably in the first month, more of these devices sold than in our customer base than any other persistent memory device. So that's pretty cool. It also has probably one of the worst names ever for people that want to stay on the right side of Intel. So I liked Crystal Ridge better. Anyway, so this is the big deal. This has really changed the game for us. And to be honest, it was started in 2012 when Intel realized they had a problem, and they worked through the industry, just like CXL, in bringing in parties who had a common theme, even though there may be competition at other levels. And so that really made the difference, and it's because of the NVM twig and the programming model that we have software that we can actually run on top of our hypervisor. So I sort of go through this list here to just say, are we ready? And this is not an exhaustive list, and if I've left your company out, I apologize, it was not intentional. There's only so much you can do over a weekend. No, just kidding. So first off, the JEDEC, the people that actually define the electrical, the protocol, and the low-level register interfaces for DIMMs, they now have the various standards that are relevant for this generation of NVDIMM and Intel Optane DC persistent memory. And in the future, they will actually get ahead of the game with their specs for persistent memory across DDR5 and the support of NVDIMM-P. So that is, that's great that we're now finally, the standards committees are a little ahead of the game instead of playing catch up, but that's the way new technology works. We have the SNIA NVM programming model that Andy talked about. We've also had the ACPI non-volatile storage technology group. They've really helped to standardize the firmware interface to persistent memory for operating systems. And a lot of what we did is dependent on that. And UEFI, which represents where the forward-thinking firmware effort is, and if you're not using UEFI, you should be on your servers. They also added a number of important extensions to support persistent memory. From a device point of view, we've now got three choices. We have the NVDIMM solutions from HPE and Dell, and there are still cases where customers say, that's all I need. I just need a little bit for tail of log optimization for Microsoft SQL Server 2016. That's great, that's all I need. There are others that are looking at this more whole cloth, and they can benefit from Intel Optane DC persistent memory. So we now finally have a lot of this in place. We have a number of x86 server vendors, and I'll come back to that in a moment. And really important, we now have, as Andy described and as others, native OS support. We have Windows support, we have Linux kernel support, and there are probably other operating systems that I should mention here. But customers now have a choice of what they can deploy natively and in a virtual machine. And then finally, we have the important direct access models. Again, we've already talked about them, and those are really important because what we want to do as a hypervisor is we don't want to get in the way. We don't want to have to intercept these requests, turn around, and emulate them. We want it to be direct mapped into the VM. The VM does loads and stores just like DRAM, and it all works. So I think we're pretty good there. Hypervisors, well, we have VMware vSphere, which is why I'm up here, but we also have solutions for KVM, Hyper-V, and the Zen project. So hypervisors are supporting this also as a first-class citizen. And then lastly, this is probably the key thing. We are now finally seeing enterprise apps that can support it directly, such as SAP HANA, Microsoft SQL Server, a number of other databases. We even have providers such as Phoenix NAP working with a company called Panzera to take their Vision AI Elasticsearch tool, or I should say mechanism, and be able to use persistent memory to speed up the search. We're finally getting there, but I still think we need more applications. I think this is probably one of the biggest obstacles in getting our customers excited is we need more choice in applications that support persistent memory. And so I'm hoping that many of you here represent developers and application software companies, and I hope you are starting to see the advantage of using this technology. So let's talk about servers for a moment. Well, actually, in 2017, we didn't support persistent memory in our product. And so I can say that in 2017, we had 0 certified servers with the technology. Now in 2018, we were actually able to add support for NVDIMM-N, and this was based around the Intel Skylake, and that's another the official name is another long name, Scalable Processors Facility, blah, blah, blah. Anyway, that launched in July of 2017, and we launched vSphere 6.7 in 2018, and that represents a lot of work by a number of our people, including Rajesh, who Andy mentioned earlier. It was a pretty big deal for us. So what happened is, in that time frame, we had over 26 servers from various OEMs certified to use persistent memory. That's not bad. But when Cascade Lake launched with Intel Optane DC persistent memory in April, that number more than doubled. And so we ended up with 60 vendors who are supporting, who have certified, or I should say 60 servers certified with VMware persistent memory. That number is going to grow. So it's obvious to us that, love it or hate it, Intel Optane DC persistent memory has really been a change in the industry and driving interest in our OEMs. So I think that's pretty good. So just reviewing the model briefly is you have a native OS, say a legacy OS that knows how to use, that doesn't know anything about persistent memory, but knows how to use special drivers that can expose it. That's great. In a virtualized environment, we can make that work. And that we can do with a virtualized PMEM as a block device, as I talked about. And that requires no new driver in the guest. So that's great. And of course, we can support VMs running OSs that are much more aware. In fact, we could support VMs of different operating systems with different PMEM technologies, all using a portion of the persistent memory, the logical persistent volume that we're exposing to each of these. So that potentially allows a direct load store model with little OS overhead to the persistent memory in a VM that's running in that environment. It also allows us to bring benefits of vSphere virtualization, which we either have made available now or will be able to do later, such as multiple workloads using PMEM, being able to migrate between servers with different PMEM technologies, live VM migration across servers. We'll be able to do checkpointing, and there are a lot of other things, and there are URLs down there that you can read some of the articles on it. So I think we're there. Another part of using persistent memory is making certain that you can actually deploy applications to take advantage of it. So using, it's one thing to manually move VMs to a host that has persistent memory and has the data that you wish to operate on. It's another thing when you can actually automate it, and we can do that with vCenter and our distributed resource scheduling, so that we can automatically move those VMs and their data sets, persistent memory data sets, onto a particular host. We can also do the opposite, which is really good in the case of data protection and error remediation. You can shut down, you can move the host into a maintenance mode and shut down the VMs, and then you can actually move them off the host. And in the future, it's likely possible that you'll be able to live migrate them as well. So I think we are there. I think as an industry, we have made a lot of progress, and the reaction from customers has been overwhelming. So this is a little boy dipping his toe into the water. It's actually not been overwhelming, but we can do better. So there were great graphics of people dipping their toes, but they were all copyrighted, so I couldn't use them. Okay, so let's talk about data protection. In the near term, we're talking about a scenario where the VM has managed to boot. We in the hypervisor have managed to mount the logical volume, and there were no errors involved in that. The data looked clean. But what happens now if during the running of the VM that's using persistent memory, it runs into problems? So the first one that you can think of is, well, what if there is transient corruption? And so the VM consumes poisoned, corrupted data. What can you do? Well, in the short term right now, what we can do is we can shut down the VM. We have to do that because we don't want it to make forward progress. Assuming there is VMware HA, high availability, installed, we could potentially restart the VM on the same host where the data lives. But of course, we would scrub the affected areas where the machine check occurred to see, is it safe to start the VM? If it isn't, well, then we're not going to start it. There are also a number of other error classes that are relevant that we have worked with ACPI to be able to define, because why today the mediation might be primitive, in the future it can be much more advanced. So for example, ACPI has defined various warning alerts, such as maintenance is needed, maybe you're exceeding your endurance, or performance degradation because maybe the device is overheating. That allows us to alert the administrator to schedule maintenance to go take a look at the problem, but not shut down the server right away. Then there's a class of errors where they're a little bit more serious. And I've shortened, these aren't the actual names, I couldn't fit them in the box, but effectively there's write persistence loss that can occur effectively when you attempt to offline or shut down the server. And what that means is that effectively any writes that you've done since the time the server is booted, you are going to lose them when the server shuts down, even normally. So that's a pretty serious thing. Or all data loss means if you shut down the device or shut down the server, the next time you bring that device up or you restart the server, not only will you have lost data that you might have written before, you're not going to be able to potentially read it reliably also. That's a pretty big concern. And then lastly, there is, if a power loss happens now, you're not going to be able to read or write anything the next time you boot, the next time you bring the device online. Those are pretty serious. So today, what we can do, or I should say what we hopefully be able to do in the future, is we can automatically shut down the affected VM, and then we're going to wave our hands at the administrator because they're going to have to take some serious steps. The administrator is going to have to shut down all the VMs. We can auto shut down the affected VMs, but he's going to have to shut down all the VMs to put the machine in maintenance mode. This doesn't require a reboot. And then the administrator will have to make a choice about, do I start migration, moving the persistent memory data set and the VM to someplace else? And you'll have to reboot. Another case is basically you're going to lose write persistency at a power loss. So all the writes that you've done since the time it booted will not be saved. So you'll lose them if a power loss comes by. Or basically write persistency lost now. So all the writes you did before the event are good. All the writes you're going to do afterwards are going to be lost if the system shuts down or loses power. And in that case, in the simplest case, we can just shut down the affected VM and we go through the same flow. What can we do better in the future is in the case where the VM crashes or the VM actually gets a consumed poison, it may be possible to actually reflect that machine check back to the VM and allow the guest operating system to try to deal with that. So rather than shutting it down because we don't think the guest knows how to deal with it, we think that in the future, the operating systems and the application stacks using persistent memory are going to be smart enough to actually deal with this more intelligently. So we don't have to shoot the VM in the head. The other case is mostly the same, but in the case of the write persistency case, this middle box here, we can certainly auto-suspend or shut down, and we could even do potentially a live migration, or at least a cold migration of that VM off the server much faster than an admin who has to jump into maintenance mode to do it. And so this could be a great saver as well. We also have cases where, as we discussed before, where yes, we should suspend or shut down the VM. We have a little bit more time before we have to move it because our data is good at the moment, but new data isn't going to work, which is why we had to shut it down or suspend. And again, you can live migrate it or cold migrate it, and that seems like a pretty good thing. Now, hopefully you're also, in the future, we would expect that there would be a checkpointing or replication solution in the background that will be able to back up PM every so often to some external resource. That's going to be pretty important, because if you don't have that, the last class of error has a very special remediation. And you want to try to avoid that as much as possible. Okay, so one of our experiences has been that server hardware and firmware for PM was a real firestorm between 2017 and 2019. The specs were trying to struggle against hardware schedules. Thanks to Intel, error detection and remediation sort of changed at the last minute. And there were just too many iterations with OEMs, server OEMs, to get this right. We did it, but it was a lot of pain. And the provisioning and encryption is still pretty non-standard. This shouldn't happen in 2020. One, the firmware interfaces are now more mature and stable. And I can say this because there was a public Intel slide. Intel Barlow Pass doesn't seem to screw it up much, so that's good. And OEMs now have experience deploying real solutions, so that's really good. Also, we've been a little bit more defensive. We now have a full PMEM certification kit for OEMs to really test out a number of the error scenarios I showed you on the previous page in order to help us test our code and to make certain that the OEM is doing the right thing. But I will say that these architected firmware interfaces are critical to OS and hypervisors, and we will only certify a PM solution in combination with a platform that supports it. Okay, so I have a choice here between persistence and I'm going to go with just assume that there will be more interesting solutions in the future for persistence. And I apologize, I'm not going to be able to hit this in the time I've got left. Well, I could try briefly. So one of the key problems that Andy mentioned was this optimized flush. So you've got the data sitting in the cache of the processor, and the optimized flush moves it from the cache into a special structure in the integrated memory controller called the write pending queue. So that's great, and the right way to do that today is with a cache flush operation. Now, what do you do, however, if you lose power in that case? So a number of smart server people and Intel have defined a mechanism called a synchronous DRAM refresh. And what happens is a platform can inject a signal into the processor, and if the platform provides enough energy reserve, the processor will dump its write pending queues out to DRAM, including to persistent memory. And so in the case of an NVDIMM device, it will end up in the DRAM of the NVDIMM device. And in the case of an Intel persistent memory device, it will effectively end up in the media. So that's a little bit of additional energy reserve and maybe a period of time that's under a few milliseconds. And this is standard in all persistent memory servers that VMware supports. So it's a good thing. Now, you still have the problem of, for NVDIMM-N, how do you get it from the DRAM into the NAND device? And this is why you see this requires a supercap or another energy reserve in order to be able to do this. And today, you'll see integrated solutions where this actually, there are traces on the board that come up through the DIMM connector that supply this power to do this. In the future, it's possible in systems that have really large energy reserves that you could actually have the processor automatically flush the caches into the write pending queue and use ADR to kick it over to the device. Right now, that solution is BIOS, issuing special instructions. And this has been shown, for example, in the HPE Scalable Persistent Memory solution. So that's something you can do. Thank you very much. Okay. That's something you can do, but it's still a little bit exotic, and I think it's going to take some time. You can certainly imagine if you can write BIOS to do these kinds of operations, you can optimize it even further with hardware state machines and other kinds of embedded mechanisms, such that you may be able to cut down that time significantly in milliseconds, and the energy reserve might not be as large. That's going to be really good. I don't have time really to talk about persistent memory pooling, but as other speakers have mentioned, with CXL and Gen Z, you actually have the opportunity, because these are coherent I/O, and coherency is very important. You assume it without even realizing it. With the coherent I/O interconnects, you can actually take your persistent memory and place it on a remote device. Maybe, in some manner, maybe it's an I/O device that's either plugged into a slot on the server, or it's a device that lives in a centralized resource. Perhaps it's a CXL.mem device, and you could even have it behind a switch. Putting it behind a switch allows you basically to sort of do failover as well as load balancing. The failover is if one server dies, but you've managed to at least make its writes hit the shared device, then you can, with the assistance of a fabric manager or an orchestrator, fail it over to a different server, and you haven't lost much. Also, there's the opportunity to load balance. So if you have, say, 32 terabytes of persistent memory here, you can choose, I want to give 6 terabytes to this server and 10 terabytes to this, and I want to hold the rest in reserve. These are the kinds of games you can play with CXL or Gen Z, which will have native support or very near native support in the future. This is a future that we're pretty excited about. I'll just say that on capacity, it's going to grow. It would not be a surprise to see maybe 2 terabyte devices in the next 5 years. It wouldn't be a surprise to see that a 2-socket server could have 16 or 32 terabytes of persistent memory. And there are a lot of new technologies coming, but my message to hardware vendors is there needs to be one standard OS software interface, or we're going to screw it up. And that's good. It's good to know that Andy and others are already working on that next generation. So in summary, we are ready enough, but we will learn much in 2020. We need more applications. We need to change the customer and developer perception. And in the future, we expect a lot of collaborative work in the industry on data protection, server firmware and hardware, and persistence domain and power loss. And you can see hardware innovation for future topologies and technologies are really going to be a big game changer. With that, I'll end. I've used up all my time for questions, but thank you very much.
Kia Kettridge.